A very good morning to all of you. I cordially welcome you all for this engineering thermodynamics course. So today's classroom discussion topics are how can we find out availability in a steady flow process, and similarly availability equation for a flow and non-flow processes. So the motivation behind these topics are it is very essential to apply availability equation for a flow process and non-flow process to assess their performance. So the outcome of the today's lecture is so you should be able to apply availability equation for a flow and non-flow processes after completion of this lecture. So already I told you that how can we define the availability. So it is nothing but the maximum useful work that can be obtained from a heat engine, that is known as the availability. So now the topic here is availability in a steady flow process. So because I told you that steady flow is nothing but is open systems. Almost all engineering devices are examples for the open systems. So we have to apply the steady flow energy equation. That is, the steady state is nothing but the thermodynamic parameters will not change with respect to the time. So then we can say that the system attains the steady state condition. So availability in a steady flow process. So now always I am referring to the steady flow energy equation here. So that is the exit values. I have taken it as the atmospheric level, that is instead of H2 I am writing down H0 because these are the system is in the thermodynamic equilibrium with respect to the surrounding atmosphere temperature. So at the dead state conditions we can say that the temperature is equivalent to T0 and enthalpy is equivalent to H0 and entropy is equivalent to S0 like that. So the W max from the steady flow energy equation, so it is nothing but H1 is enthalpy at the inlet and H0 enthalpy of the working fluid at the exit. C1, so C1 is nothing but is the velocity of the fluid at the inlet condition, and Z1, that is the datum level at the inlet condition. So he has given clearly that the Z0 value will be equivalent to 0, which can be taken at the exit from the operators. Z0 will be equivalent to 0. So that's why here we have not considered any Z2 value. So that's why here we are considering only the initial level, the datum height. So from which we are able to say that the W max is equivalent to H1 minus T0 S1 minus H0 minus T0 into S0 whenever we are neglecting the changes in the kinetic energy and potential energy. So that is, it is the basic equation to find out the availability in a steady flow process. So that is H1 minus T0 S1 minus H0 minus T0 S0. So simply we can call it as B minus B0. So in the examination, he will ask you derive the steady flow availability function. So instead of asking availability in a steady flow process, he can ask the question in another manner, that is derive the steady flow availability function. So what do you mean by the steady flow availability function is this is H minus T naught into S. So H minus T naught into S, that is known as the B. So this particular the B is known as the steady flow availability function, which is also known as Keenan function, which is also known as is a Keenan function. So the steady flow availability function and Keenan function represents what? It is the difference of enthalpy and the product of the environment temperature and entropy value. So it is H minus T naught into S that denotes the steady flow availability function or the Keenan function. So like this we are able to derive the availability in a steady flow process. Now the availability in a non-flow process. So how can we find out the availability in a non-flow? Because now we studied the flow. Now let us come to the non-flow process. So in the non-flow process also once again, so we have to deal with this particular the entropy equation. So that is here from that particular the first law of thermodynamics and the second law of thermodynamics combination. So here we are able to derive that the maximum work that can be obtainable from the non-flow process is equivalent to U plus P naught V minus T naught into S. That is, one stands for the inlet condition and naught stands for the environmental conditions. So here we can say that W max is equivalent to A1 minus A2, where A stands for non-flow availability function. So in the previous case, B stands for the steady flow availability function, but here it is the A stands for is a non-flow availability function. So how can we define the non-flow availability function? It is nothing but U plus P naught V minus T naught into S. So in the previous one, in the steady flow availability function, so that is here the B. So B is representing what? Steady flow availability function, that is H minus T naught into S. And here A is representing here the non-flow availability function, that is U plus P naught V minus T naught into S. So like this, we are able to determine the availability in a steady flow process as well as in a non-flow process. So now based on this particular the concepts, now let us solve some problems which were previously asked in the GATE examination. So first one is calculate the decrease in available energy when 20 kgs of water at 90 degrees centigrade mixes with 30 kgs of water at 30 degrees centigrade. So now here we are having the two working fluids, that is both are water only, but both are available at different temperatures and at different quantities. So the initial quantity of the water is 20 kgs, that is the M1, and T1 is equivalent to 90 degrees centigrade. So always you have to convert into the absolute temperature Kelvin. So and M2 is 30 kgs of water and T2 is equivalent to 30 degrees centigrade. And here he has mentioned that the pressure being taken as constant, so constant pressure process, and the temperature of the surroundings is 10 degrees centigrade. So it is the T naught. So T naught value as given as 10 degrees centigrade. And we know that the Cp of the water is always equivalent to 4.18 kilojoules per kg Kelvin. So for any problem, first of all, you have to write down the given data. And I already told you that always you have to convert the Celsius into the Lord Kelvin absolute temperature. So then you find out the available energy because he's asking us to calculate the available energy. So what is the formula to calculate the available energy? So this is the formula. So that is MCP integration from initial temperature of the T naught to final temperature of the T, 1 minus T naught by T into dt. So it is the formula to calculate the available energy, which is nothing but available energy is nothing but what? Efficiency, because efficiency is equivalent to work done divided by the heat supplied. Efficiency is equivalent to work done by the heat supplied. So W is equivalent to what? Efficiency into heat supplied. So efficiency into heat supplied. So heat supplied is nothing but MCP into delta T. MCP into delta T. So like that we are able to have the available energy equation. So let us find out first of all available energy for the initial quantity of the water, that is 20 kgs of water at the 90 degrees centigrade. So M you take it as 20, Cp as 4.18, and the initial, that is the surrounding temperatures are at the 10 degrees centigrade and the water is available at the 90 degrees centigrade. So plus 273, 1 minus T naught by T. So T naught value is known to you by T into dt. So just you integrate. By integrating this, you are able to obtain the value of the available energy which is there in the 20 kgs of the water. It is equivalent to 798.38 kilojoules. Now similarly you find out how much amount of the available energy is there in the 30 kgs of the water at 30 degrees centigrade. So by using the same formula, now you are able to obtain the available energy in 30 kgs of the water is equivalent to 85.27 kilojoules. Now how can you find out the total available energy? That is the available energy of the 20 kgs plus available energy of the 30 kgs, that will give you 883.65 kilojoules. So actually these two fluids are mixing with each other. So the first fluid, that is the water, is available at the 90 degrees centigrade and another water is there at the 30 degrees centigrade. So whenever these two are mixing with each other, so automatically it will reach a final temperature. So we have to find out what is the final temperature after mixing of these two fluids which are there at different temperatures. So now for this particular purpose, we have to find out the final temperature value after mixing. So how can we find out the same thing? The MCP delta T and MCP delta T, that is heat lost by the hot fluid is equivalent to heat gained by the cold fluid according to the energy balance. So initially it is there 20 kgs, so Cp value is same, delta T, that is initially the water is there at 90 degrees centigrade temperature. Now we have to find out the intermediate temperature after the mixing. So now the another fluid is there at the 30 kgs and it is available at the 30 degrees centigrade. So heat lost by the hot fluid is equivalent to heat gained by the cold fluid, that is energy balance. From this we can find out what is the temperature value. So temperature value is equivalent to 54 degrees centigrade after mixing of two working fluids. And similarly, the total mass after mixing, that is a 20 initially, 30 later. So 20 plus 30 is equivalent to 50 kgs. Now, by using the same formula, now you can find out the available energy of the total mass, that is equivalent to 50 kgs. The temperature is 54 degrees centigrade by using the same formula. So here we are able to have the total available energy after mixing is equivalent to 649.99 kilojoules. Now, how can we find out the decrease in the available energy due to the mixing process? That is the total energy before mixing process minus total energy after mixing process. And already we find out the total energy before mixing process is equivalent to 883.65. So it is the before mixing. So it is the available energy is 883.65 kilojoules. And now after mixing you are able to have 649. So the decrease in the available energy due to the mixing process is equivalent to how much? 233.66 kilojoules. And why it is decreased available energy? Because the mixing process is always leads to an irreversible process. So whenever it is leading to the irreversible process, so more losses we are able to encounter. So automatically the maximum work potential will be gradually reduces. So that's why we are able to witness the available energy value is basically decreasing due to the irreversibility process of mixing. So this much amount of the work is lost due to the mixing of two working fluids. That is the gist from this particular problem. So like this, we are able to solve some problems based upon the availability in a steady flow process and for a non-flow process, because these are the very, very important concepts. Always one question will come based upon the availability of a steady flow process and non-flow process. So always you have to remember the steady flow availability function, that is the B is equivalent to H minus T naught into S. And similarly non-flow availability function also always you have to remember, that is the U plus P naught V minus T naught into S. So these are the two important functions we are able to derive from the today's class. So thank you one and all for listening to today's classroom discussion topic about the available energy of a steady flow and non-flow process. Thank you.